Let's look now at section 3.2 and give an introduction to polynomial functions. In the last section, we saw the graphs of quadratic functions, and in particular, the details that are required to take a simple sketch of a parent function into a fully detailed graph. In this section, we're going to be looking at more functions. In particular, we're going to be looking at polynomial functions. So let's start off with a definition. Let's let n be a whole number. And a sub 0, a sub 1, a sub 2, comma, all the way up to a sub n, let's let those be real numbers. These can be any real numbers. With a single restriction, we need a sub n not to be 0. The function f of x is equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot, plus a sub 2x squared, plus a sub 1x, plus a sub 0, is called a polynomial function of degree n. Okay, so a few things to mention here. In particular, let's talk about these. A sub 0. Sub 0. This is the first time I ever heard this. I thought, what does a character from Mortal Kombat have to do with anything? Here, these are called subscripts. That's not a math term. That's a typesetting term. A subscript is just a number or a character or a symbol that's written down below the line of the main text. So you have a letter, say for example A. If you write something up here, that's a superscript. We write exponents as superscripts. But instead of writing it up and to the right, if we write it down and to the right, that's called a subscript. Superscript versus subscripts. Whenever we write a small number as a superscript, that's a power. Second power, third power, fourth power. When we write it as a subscript, it means something else. These are labels. This means this is the 0th one. This is the first of these. This is the second of these, the third of these, the fourth of these, and so forth and so on. Now you say, okay, so you're just counting. You're saying that's the first one, second one, third one. Why did you start counting at 0 though? I mean, I guess you could. There's nothing that says you can't start counting at 0, but don't you usually start counting at 1? Well, there's a reason we want to start counting at 0. Notice right here, a sub 0, a sub 1, a sub 2. These numbers are going to be the coefficients of a polynomial. After all, this is going to be like the number 5. This will be 2x and 7x squared, and so forth and so on. These are coefficients. The way we've labeled these, the subscript tells you which powered variable this coefficient belongs to. In other words, a sub 2 is the coefficient of x to the power 2. A sub 1 is the coefficient of x to the power 1. Here, a sub n is the coefficient of x to the power n. So that's what these little numbers are for. They help label these coefficients as belonging to a particular powered term. A sub 2 is the coefficient of x to the 2. A sub 1 is the coefficient of x to the 1, and so forth. And that's why we start counting at 0, because that way we have a term on its own without a variable. This is the one that has no x variable, right? Hence a sub 0. All right, so here, these numbers are just the coefficients of your polynomial. Here, they can be anything, positive, negative, fraction, whole number, decimal, as long as they're real numbers. Here, the one restriction is we don't want this one to be 0, because if that one were 0, well then you could have just started with one term. You could have started one term later. All right, you could have started with this one. And here, we want this one to be not 0. We do want this one to be there, because this is what gives this polynomial its designation. This is a polynomial function of degree n, because n is the highest power. If this is 0, well then this isn't really there, so n isn't the highest power. All right? So a polynomial function of degree n is simply a function that looks like this, with the biggest power being n. Now, of course, n can be any number we like or any number we need. So for example, let's say you have the polynomial function f of x is equal to 7x to the 4th power minus 6x squared plus 17x minus 12. Here, this is a polynomial function of degree 4, because here your greatest power on any of these terms is power 4. So this is a polynomial function of degree 4. The degree of a polynomial is actually a very important piece of information. By itself, it'll actually tell you a good amount about our functions and its graphs. Okay? Let's look at one more. G of x is equal to 3x to the 9th power plus 12x to the 7th power minus 16x to the 5th power plus 8x to the 12th power plus 17. Okay? Here, this is your greatest power term. So this is a polynomial function of degree 12. Usually we write our polynomials in descending order. When we say descending order, we mean from the biggest power down to the smallest. If ever it's not written in descending order, that doesn't change its degree. It just means that for some reason, maybe just as an oversight, maybe we overlooked something, it was written out of order. So here, the proper way to write this one would be in descending order. Start with the term that has the biggest power and then work your way down. Power 9, then power 7, then power 5, and then the one without a power, without a variable, like that. Okay? So here, the fact that this was in a different order doesn't change that this is a polynomial function of degree 12. So it's not really the first term, it's the term with the biggest power. That being said, usually we do write the term with the biggest power first. So this is a polynomial function of degree 12. Now, in the previous section, we saw that when we graph quadratic functions, we're going to want to find the vertex, we're going to find the x-intercept, and the y-intercepts. When we graph a polynomial function, a generic polynomial function, we're going to find something similar. To graph a polynomial function, we find, well, much of the same thing. We're going to find the y-intercept. We're going to find the x-intercepts, and it is possible to have more than one x-intercept. So I'll put it in parentheses, x-intercept or intercepts. Y-intercept, you're never going to have more than one, because if you have more than one y-intercept, that means you cross the y-axis more than once, which means you have 2 points that are right on top of each other, and therefore you don't have a function anymore. And here, since we're talking about functions, that's not going to happen for us. So here, you can never have more than one y-intercept, but you can have more than one x-intercept. Now, for a parabola, we were looking for a vertex. However, remember, a vertex is the point that is the lowest on a parabola that points upwards, or the highest on a parabola that points downward. That's called the vertex. For a generic polynomial function, you probably won't have this shape at all. It won't look anything like this. So asking for what is the highest or the lowest point, or the point where your graph turns around, or something like that, probably won't make sense for a generic polynomial function. For a very specific polynomial function, particularly for a quadratic, yeah, of course it makes sense. We've already seen that. But in general, that is not a useful or maybe even a possible thing to find. So here, we're still going to find more information, but a vertex will not be one of them. What we are going to look at is what's called the end behavior of a function. The end behavior will be determined entirely, I was going to say largely, it's going to be determined entirely by the lead term. Now remember, we want the term with the biggest power to be the lead term. So if ever you have something that's not in descending order, we should write it that way first, meaning the term that tells you which degree, that one should be in the front. So here the y-intercept, that's still going to be found by setting x equal to 0. The x-intercepts are still going to be found by setting y equal to 0. The end behavior is going to be found by the lead term. Okay, so how does the lead term do that? What does the end behavior look like? How does that tell us that piece of information? So before we talk about that, we're going to need to express something in a particular set of symbols, using a particular set of symbols, and these might be new to you. So let's go ahead and take a moment to describe and talk about what these symbols say and mean. So the symbols that we're going to be looking at, they are somewhat familiar, but you may not have ever seen them quite this way. Okay, so you're familiar with the infinity symbol. That means you're going forever in one direction, right? Positive infinity or negative infinity. You know what x is, that's a variable. But here we have an arrow. So x arrow infinity. The way you would read this is x approaches infinity. Now, obviously, x can never be infinity because infinity is not a number. X can be 5, it can be 50, it can be 4 billion, it can be as big a number as I want, but it can never be infinity because infinity is not a number. When we say x approaches infinity, that's a manner of speaking to say let x get bigger and bigger and bigger without ever stopping. So what we're saying here, we're not saying x equals to any one thing in particular. What we're saying is, okay, keep substituting numbers and let those numbers keep getting bigger. Let x be 1,000,000, then 1,000,000,000, then 1,000,000,000,000. We're not looking for any particular number, rather we're looking for a pattern. What happens as x gets bigger? That's what this means. As x keeps getting bigger, without ever ending, or without ever reaching a maximum, as x keeps getting bigger, what happens? We have a similar symbol for going in the other direction. This is read as x approaches negative infinity. And it does the same thing, except here it says, instead of letting x become greater and greater numbers, here it's becoming lesser and lesser numbers toward negative infinity on the left. And this is read as x approaches negative infinity. Okay. Now, our x variable can approach either infinity or negative infinity, meaning let x keep going to the right, or let x keep going to the left. But we have, when we're dealing with a function, our x is tied to our y value. So that's what we want to do. We want to say, as our x value keeps getting more to the right, what's happening to our y value? Well, depending on our function, and in fact, we'll see some more of these at the end of chapter 4, at the end of chapter 3 and in chapter 4, it might be coming closer to a particular number. However, with polynomials, generally, if x gets really, really big, so does y. We'll hold off on that until later in chapter 3 and at the end of chapter and inside of chapter 4. But in fact, we will see some cases later where if x gets really big, y might become the number 5 or something like that. But for polynomials, what's going to happen is x gets big, y is going to get really big. Or maybe the other way around. If x gets really big, maybe y will become very negative. It'll become lesser and lesser. So the symbols for those are going to be similar to the symbols for x, and that's going to be f of x is either going to approach infinity or it's going to approach negative infinity. And this is one of those things that is somewhat strange, but I'm actually very proud of the way that arrow came out. Look at how ugly these are. These came out lopsided and crooked, but that one's so nice. It almost looks like I typed it. That's the kind of thing I'm proud of. So here, this is read as f of x approaches infinity. And really that just means the y value. And this one is read as f of x approaches negative infinity. All right, so with this language, we can now talk about how the lead term determines our end behavior. Our textbook calls this the leading term test. Let f of x be given as a polynomial function a sub n x to the power n plus ... plus a sub 2 x squared plus a sub 1 x plus a sub 0. Here, this is called the leading term test because that's the only one that's going to matter. So let's start off with this. The end behavior of this function will depend entirely on what is the sign of this lead coefficient and this power, is it even or odd? Note that there is no computation to do. You're not going to find anything by computing anything. It's simply a matter of recognizing what's already there. So there's going to be 4 possibilities. If a sub n is, let me start off with this. If n is even, so this power right here, if this is the power 2, 4, 6, 8, 10, 12, any even number, if n is even and a sub n is greater than 0, so this is even and this is positive, then as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x will approach infinity as well. Say what now? What this means is, if this is an even number and this is a positive number, as your x value goes further and further to the right, the y value will get higher and higher. Okay, so your graph, as you move further to the right, will get higher and higher. As your x value moves further to the left, to negative infinity, your y value will also go to infinity. It will also get higher. This is called the end behavior of the graph. What we don't yet know is what happens in the middle. Okay, maybe these just connect as a nice smooth line. Or maybe there'll be a little bit of a wiggle. Or maybe there'll be a very jagged edges in here and very pointy. Or maybe it'll just come down a little bit and then go up a lot. Or we don't know. We have no idea what happens in between here. But what we do know is on the ends of the graph, as you go to the right, it's going to go up. And as you go to the left, it's also going to go up. That's what this means. So this is one possibility. The other 3 possibilities are going to be very similar to this. If n is even and a sub n is less than 0, so that's an even number, but now this is negative, then as x approaches infinity, f of x will approach negative infinity. And as x approaches negative infinity, f of x will also approach negative infinity. Or in other words, as your x goes forever to the right, your y value will go down forever. So to the right, you go down. And as x goes to the left forever, your y value will go down forever. So as you go to the left, your y value will go down. And there we go. Again, you don't know what happens in the middle. Maybe it'll be very wavy, or maybe just a little bit, or maybe it'll just go smoothly right across. We don't know. We'll find that out later, depending on the function. But what we do know is what happens on the ends. Okay. Let's take a look at the next one. If n is odd now. We've seen both cases. If n is even. Now let's see what happens if n is odd. Well, if n is odd, you can either have your coefficient be positive or negative. So let's take a look at what happens if it's positive. If n is an odd number and a sub n is positive, then as x approaches infinity, f of x will also approach infinity. So as you go to the right, your y value will go up. So it'll look like that, up. But the difference now is as x approaches negative infinity, f of x will also approach negative infinity. Meaning, as x goes forever to the left, your y value will go forever down. So here, this will go this way. Okay? So that's like that one, but this one's different. Okay? And finally, the very last one. If n is odd and a sub n is less than 0, so that's an odd power and that's a negative number, then as x approaches infinity, f of x will approach minus infinity. As you go to the right, your y value will go down forever. As you go to the right, your y value goes down. And as x approaches negative infinity, as you go forever to the left, your y value, f of x, will approach infinity. In other words, as you go forever to the left, your y value will go up forever. So as you go to the left, your y value will go up. And there we go. These are your 4 possible end behaviors. Note, we don't know what happens in the middle just yet, but we do know what happens on the ends. Either both go up, both go down, goes up to the right and down to the left, or down to the right and up to the left. If you think about it, those are the only possible combinations, aren't they? The only other possibility is as you go to the left or to the right, it would not go up or down. Right? If you went to the right, maybe it would go flat. That's not going to happen for a polynomial function. For polynomials, these are the only possibilities. It will be possible to have something that goes up to the right and then flat on the left, or flat to the left and up to the right, but that won't be polynomial. We'll see things like this when we look at rational functions, and we'll see something like this when we look at logarithmic and exponential functions. But for polynomials, these are our only possibilities. All right? So let's take a look at a quick example. We're not going to form a full graph. We're just looking at the end behavior. Find the end behavior of f of x equals 3x to the 5th power minus 6x squared plus 17x minus 9. Here, we're looking at the lead term, the one with the biggest power, which is usually the one in front, but be careful in case something's written out of order. And here, that's going to be an odd power and a positive coefficient, right? An odd power of n and a positive lead coefficient. Okay, so the lead coefficient, the lead term is going to be 3x to the 5th. So n equals to 5 is odd. I'm not sure why I put a comma there. So n equals to 5 is an odd number. And a sub n, which is that coefficient, is equal to 3, which is positive. Okay, so you have an odd power and a positive coefficient. You have an odd power. Okay, so it's one of these. And your coefficient is negative, positive, it's positive. Okay, so it's got to be this one. So our end behavior is it's going to go up to the right and down to the left. As your x approaches infinity, your y will approach infinity. As your x approaches negative infinity, your f of x, your y, will approach negative infinity. And there we go. That's your end behavior. Do note that your function should be written this way. If it's not, you're going to have to write it this way, or at the very least, write the first term this way. So same kind of question, find the end behavior. Let's say we have f of x is equal to, let's say 5 times x plus 3 quantity squared times, let's say 4x minus 1 to the power of 3. Okay, so now this isn't going to work the same way as this one did, because here I don't have my polynomial written out as a sum or difference of individual terms. Here it's been factored out. So I have one option, of course, is just multiply all this out. I can say x plus 3 times x plus 3. I could say 4x minus 1 times 4x minus 1 times 4x minus 1, 3 times, yeah. And then multiply all of those three things together. Or I guess I should say 3 here, 2, that's 5 polynomial terms, or 5 polynomial factors times the number 5. And that will get me a polynomial function written this way. And that's going to take a while. It's going to take a bit of effort. So that is one way to do it, though. Another way to do it, it might be a little more convenient, is to note that you only care about the lead term. All right? So right here, okay, that's the number 5. Okay, don't worry about that. X plus 3 squared. When I multiply that out, that's going to be x squared plus some other stuff. And you say, well, don't you want to be more specific? Not really. That's all I care about. That's the one with the biggest power. So it won't really matter what happens to all the other ones. All the other ones don't tell me anything about my end behavior. Same thing with this one. 4x to the power 3. That's going to give me, well, let's see, 4 to the third power. That's going to be 64. X to the third power. Plus, and now I should start distributing. Well, yeah, but all the rest of them aren't going to give me any terms that are that power. So all the other ones are ones I don't really care about. If that's not very convincing, here, let me go ahead and do that, just this part out. Let me start doing it out the long way, just to show what that looks like. If I had, and this isn't something you need to do, but just as an illustration as to why that works, let's say I have 4x minus 1 to the power 3. Well, that's 4x minus 1 times 4x minus 1 times 4x minus 1. If I were to multiply all that out, that's going to be, let's see, that's 16x squared. And then that's minus 4x. That's minus another 4x. And double negative makes that a positive 1. And if I combine my like terms, that's going to be 16x squared minus 8x plus 1. And then don't forget, you're multiplying that by another 4x minus 1. And now if I start multiplying those out, that's going to be 16x squared times 4x. That's going to be 64x to the third power. And then if I multiply this one, that's going to be minus 16x squared. Now if I multiply both of those, that's going to give me minus 32x squared and plus 8x. And finally, if I distribute that 1, that's going to give me plus 4x minus 1. But notice that in the end, all of these other terms are smaller in power than this one. So the lead term is going to come from this one right here. None of these mattered. So right here, the only term that actually mattered to me was 4x times 4x times 4x. So here, 4x to the third is 64x to the third plus, and I didn't know what those numbers were before, but notice they don't matter. Same thing over here. If I multiply this out, I'm going to get x squared plus, right, x squared plus, and I don't really care about the other terms, not for the purposes of end behavior. So now I know I have 5 times x squared plus some stuff times 64x to the third plus some stuff. But again, I don't really care about that stuff. If I just multiply out the biggest powered terms of each factor, that's going to be 5 times x squared times 64x to the third. Okay, well, 5 times 64, that's going to be 320. X squared times x to the third is x to the fifth. And then plus a bunch of other stuff which we don't really care about. Hey, that right there, that's your lead term. So it's got a positive coefficient and an odd power. Positive coefficient and an odd power. So that's this one right here. Odd power, positive coefficient. Oh, it's got the same end behavior as this one did. That was not intentional. I just picked some polynomial at random. And there we go. Note that here I went through and did a good amount of computation. Remember, that's not really necessary. This is me showing you why that was the only term that mattered, because it was the only one that had the biggest power. But note that it doesn't take anywhere near that much effort. Let me do one more. Oh, in fact, maybe you maybe try this one. Go ahead and find the end behavior of the following two functions. Try f of x equals negative 6x to the power 3 minus 8x to the power 2 plus 6x minus 12. Go ahead and find the end behavior of that one, as well as g of x is equal to, let's say, 3 times x minus 5 quantity squared times 2x minus 1 times, let's say, to the power 3 times x plus 9. Okay. Again, you're not graphing anything. You're not solving for anything. You're finding the end behavior. Go ahead and give that a try. Pause the video. And once you have your end behavior, go ahead and unpause the video and we'll go through it together. All right, so for that first one, we don't really have anything to do. Just look at the power, look at the term with the biggest power. That's an odd power. Okay, so it's one of these two. And the lead coefficient is negative. Okay, so an odd power and the coefficient is less than 0. It's negative. Okay, this is your end behavior right here. Your n is equal to 3, which is odd. And your a sub n is equal to negative 6, which is less than 0. It's negative. So that means that your end behavior is going to go down to the right and up to the left. And there we go. That's our end behavior. We don't know what happens in between these two ends. We don't know if this just comes up smoothly or if there's a bunch of waves in there or what else happens in the middle, but we know the ends. This one over here, again, it's not written in this nice form, but we can write it in this nice form. But we don't need to write it in that form. All we really need is the lead term. So right here, this is 3. If I were to square this, that would be x squared plus, and there's a bunch of other stuff which I don't really care about. If I took 2x minus 1 and raised it to the third, well, let's see, 2x to the third would be 8, x to the power 3. And then I have a bunch of other terms which I don't care about. I only care about the first one, the one with the biggest power. If I raise this to the third, I get 8x cubed plus stuff, which I don't care about. And then here, that's x, and here, I know it's x plus 9, but again, I don't really care about the other stuff. I just care about the x, the one with the biggest power. So now if I put all that together, let's see, the numbers, 8 times 3 is 24. X squared times x to the third is x to the fifth. Oh, and then one more x, that's x to the sixth. Plus some other stuff, which again, we don't really care about. So here we know our n is the number 3. Oh, sorry, it's the number 6, which is an even number. And you know your a sub n is that coefficient 24, which is greater than 0. So now we have an even power and a positive coefficient. Okay, an even power and our coefficient is positive. So here it's going to go up and up in both directions. So our end behavior for G is going to be up to the left and to the right as well. And there we go. Now, aside from finding the end behavior of a function, we're going to need two other things to graph. I mentioned already, aside from the end behavior, we're going to need the y-intercept and we're going to need the x-intercepts. The y-intercept is never going to be very difficult. All you're going to do is you're going to plug in x equals to 0 into your function and simplify. What can be more complicated is finding the x-intercepts, because then you're going to take your function, set this equal to 0, and now you have to solve that equation. If this was a quadratic, you'd have lots of options. Use a quadratic formula, complete and extract the square, but when it's not a quadratic, the only real choice is to factor. We've seen plenty of times before that factoring can be difficult. It can be a long process, and for some polynomials, it's not really possible. In the coming sections, we're going to see some more advanced factoring techniques, some factoring techniques that we haven't seen before this course. They're not usually shown in high school. They're not usually shown in pre-algebra classes. So we're going to be showing some more advanced factoring techniques, some that are a little bit longer than what you might be used to, but which are adaptable enough and good enough to factor out some much bigger and more complicated polynomials. For right now, we're going to deal with some that are factorable in the traditional sense. That is to say, using the normal factoring techniques that we usually use. Grouping, factoring out a common factor, and things like that. But keep in mind that in the next few sections, we're going to look at some examples where that won't be sufficient and we'll be factoring a different way. But regardless of what factoring technique we use, ultimately it comes down to we're going to need to factor. So let's take a look at some examples here of what we want to do. And in particular, let's talk about the language of what we are trying to do. Let's make sure we can speak about things appropriately. So let's say we have a polynomial function, f of x equals to x to the 6th power plus 2x to the 5th power minus 4x to the 4th power minus 8x to the 3rd power. So now the question is going to be find the zeros of the function and their multiplicities. Okay. Find the zeros. When you hear the phrase the zeros, what that means is take your function, set that equal to 0, and solve. Find the zeros is a short way of saying take this function, namely x to the 6th plus 2x to the 5th minus 4x to the 4th minus 8x to the 3rd equals to y. And instead of saying equals to y, we're going to set the whole thing equal to 0. That's what it means to find the zeros. Take your function, set y equal to 0, and then solve. Okay. What about multiplicities? Let's solve, and then we'll see the multiplicities at the end. Okay. We don't need to know what that word means ahead of time. We'll see what it means at the end once we have the answers. Okay, so in order to solve this is not a quadratic, so the quadratic formula is completely useless here. But what we can do is we can fall back on other factoring techniques that we've seen in the past. In particular, you'll notice that all of these terms have multiple factors of x, which means that you can factor out x to a power. In this case, they all have x to the 3rd power or higher, which means x to the 3rd is the common factor. So let's factor that out. X to the 3rd. If I factor out x to the 3rd, that means each of these terms gets divided by x to the 3rd, which leaves me x to the 3rd plus 2x squared minus 4x minus 8 is equal to 0. Okay. All right, so we take out a common factor. The next thing we want to do is, well, note that this has 4 separate terms. Whenever you have something with 4 separate terms, grouping is a good option. It doesn't have to work, but it's one that is more likely to work. So I'm going to go ahead and do this over here on the side. If I have x to the third plus 2x squared minus 4x minus 8, to factor by grouping, I'm going to take the first 2 terms and bunch them together in parentheses, x to the third plus 2x squared plus, and then the second 2 terms, I'm going to bunch them together. That's minus 4x minus 8, like that. And now I'm going to take out the common factor of just the first 2 terms. I notice I have an x squared as a common factor for both of those. So I can write that as x squared times x plus 2. Notice if you multiply those back out, that's x to the third plus 2x squared. Out of these 2 terms, I notice that both of them are negative, and they can both be divided by 4. So let me factor out a negative 4. And when I factor out negative 4 from each of those, I'm left with x plus 2. Okay? And now, here, I notice that I have x plus 2 as a common factor to both of these terms. So x plus 2 can be factored out. And if I factor out x plus 2 from this term and from this term, I'm left with an x squared minus 4. So that's an example of factoring by grouping, which means this right here factors as, well, let's leave our x to the third the way it was. And now this factors as x plus 2 times x squared minus 4. Okay. Now, it equals to 0. Now, this can be factored a little bit more as well. That's the difference of squares. That's the difference of squares. What do we square to get x to the second power? Well, we square an x. What do we square to get 4? Well, we square a 2. Okay, so to complete the factoring of a difference of squares, stick a plus in one and stick a minus in the other. And there we go. We're all done. Notice that these are the same, so we can write them together. That's x to the third. That's x plus 2 times x plus 2, which is x plus 2 squared. And then that's x minus 2. So now we can go ahead and solve. Here, if x to the third is equal to 0, well, that's just the same as saying x is equal to 0. Oh, there we go. That's a solution. This is called a 0 of my function. In this case, 0 is a 0. Doesn't have to be, but in this case it is. Over here, if I say x plus 2 squared is equal to 0, well, that's just the same as saying x plus 2 is equal to 0. Right? If x plus 2 is equal to 0, 0 squared is 0. If x plus 2 is not 0, squaring it's not going to make it a 0. So if this thing is equal to 0, that means the thing in the parentheses was equal to 0. Oh, but now I can subtract 2 from both sides, and that'll get me x is equal to minus 2. And there we go. That's another 0. So 0 is a 0 of f. Negative 2 is a 0 of f. And then this one right here, if I have x minus 2 is equal to 0, I can add 2 to both sides, and I get x is equal to 2. So those are my zeros. Now, what about multiplicities? Multiplicities have to do with how many times those zeros occur in my function. What I mean by that is, note that this right here, I wrote this as a power of 2. But I didn't have to. I chose to write it together for convenience sake. Instead of having it written out with extra terms, I chose to write it as x plus 2 to the power 2. But here, if I say negative 2 is a solution, that's because plugging it into a factor makes that factor into a 0. But notice, if I plug that in here, that makes this function 0. But if I plug it in here, that makes that 0 also. So here, this solution, this 0 of this function, works in 2 different factors. So the way we say that is that this 0 has a multiplicity of 2. because it occurs for two separate factors. If you write it this way, it's actually fairly simple because all you have to do is look at the power. Here, -2 is a 0 because it makes this factor into a 0. Oh, but the power of this is 2. Okay, so then it's got a multiplicity of 2. Here, this is a 0 because it makes this factor equal 0. Oh, but the power of this is 1, which means this only works in one factor. So its multiplicity is 1. This one works in 3 different factors. Notice x to the third can be written as x times x times x. So here the power of 3, or writing it out as 3 separate factors, either way that tells you that this is a 0 of multiplicity 3. You can check by looking at the power. Multiplicity 3, 2, and 1. And there we go. So we found our zeros and their multiplicities. The multiplicity will tell us something about the graph when we actually go through and make it. One other thing to note, this multiplicity, okay, multiplicity 3, multiplicity 2, multiplicity 1. 3 plus 2 is 5, plus 1 more is 6. Hey, look, that was the power of my function at the very beginning. That's not a coincidence. If you add together the multiplicities of your zeros, you're going to get the power of your function. You're going to get the degree of your function. So here, if your function is degree, say for example, 17, well then if you added together all the multiplicities of all your zeros, you should get 17. Here, your degree is 6, so if you add together all the multiplicities, you should get 6. If you don't, something's wrong somewhere. So not only is it going to tell you something about your graph, it's also a nice way of double checking a few things. Remember this fact, and it's actually going to come back in a later section to tell us something a little bit more. The multiplicities add up to that power that is involved in something a little bit bigger in the coming section. All right, so let's put this all together now. We've seen some examples of how to find the end behavior of a function, and you tried a few of those. And we see an example here of how to find the zeros of a function, although really this is more of a reminder. Factoring is something you've done plenty of times before. Here, the thing that you really want to notice was this language. Oh, this is called finding the zeros, and these powers tell you the multiplicity. And also, don't forget, the multiplicities add up to tell you the power of the function. But now, let's go ahead and put those all together to create the graph of a polynomial function. So, example. Let's go ahead and graph f of x equals 9x to the 5th power plus 9x to the 4th power minus 25x to the 3rd power minus 25x squared. Okay. Whenever you're going to graph a polynomial function, the first thing you want to do is try to factor it out. If you can factor it out, a lot of what we're going to do is going to be much simpler. If you cannot factor it out, that's okay. In a later section, as I mentioned, we're going to have some new factoring techniques which are going to allow us to factor things which we couldn't before. But for right now, everything is factorable in one of the traditional ways, one of our known formulas or techniques. So go ahead and try this. You're not going to graph the whole thing, but go ahead and pause the video and factor this. Factor it down as much as you can, and once you have it completely factored, go ahead and unpause the video, and we'll go through it, and then we'll proceed even further to finish the graph. But for now, go ahead and factor that. Once you have it factored, unpause, and we'll go through it together. All right, so let's take a look. We're going to go ahead and factor this thing. And find the zeros. Okay. Really, all I asked you to do is factor, but the factoring is going to be used to find the zeros. So I'm going to go ahead and do that at the end. But really, let's just start with the factoring. Okay, so we're going to take 9x to the 5th plus 9x to the 4th minus 25x to the third minus 25x squared. And the very first thing I notice is I have a common factor. All of these are divisible by x to the second power. So let me take out that common factor of x to the second power before I do anything else. Okay. Now here, this it's got 4 terms. So I think the difference of squares may work out. Now, of course, it may not, but there's a good chance it will. So let me go ahead and do that over here. If I take 9x to the third plus 9x squared minus 25x minus 25, I can take the first 2 terms and bundle them together in parentheses. Plus, I can take the second 2 terms and bundle them together in parentheses. And now from here, I notice a common factor of 9 and x squared. So put that together as 9x squared, leaving us x plus 1. Right? 9x squared times x is 9x to the third. 9x squared times 1 is 9x squared. Here, I notice that both of these can be divided by a negative 25. So let me factor out negative 25. If I divide that by negative 25, I'm left with x, and that one will leave me 1. And finally, since I know that x plus 1 is the common factor there, I can factor that out. And if I factor out x plus 1, I'm left with 9x squared minus 25 as my other factor. So here, that's the grouping. The x squared hasn't changed, but now this has factored into x plus 1 times 9x squared minus 25. And that can be factored some more. Notice it's the difference of squares. So that's x squared times x plus 1. Here, what do we square to get 9x to the second power? Well, we square with 3x. 3x times 3x is 9x to the second power. What do we square to get 25? No, we square a 5. To complete the factoring of a difference of squares, stick a plus in one, stick a minus in the other. Okay, so there's the factorization. Okay. So to find the zeros, in fact, let me go ahead and write that in 2 separate stages. The very first step was just a factor, and there we go, we factored. So now let's go ahead and find the zeros and the multiplicities. Okay. Let's see here. So I already have the factorization. So that's going to be x squared times x plus 1 times 3x plus 5 times 3x minus 5 is equal to 0. Okay, so now I can solve this equation. I can find the zeros by taking each factor and setting it equal to 0. Well, if x squared is equal to 0, that means x is equal to 0. Okay. Notice the multiplicity. The power there is 2, so the multiplicity is 2. Okay. If I have x plus 1 is equal to 0, I can subtract 1 to the other side, and that'll give me x is equal to a negative 1. Notice the power of this one is 1, so this has a multiplicity of 1. If I have 3x plus 5 is equal to 0, I can subtract 5 over this way and then divide by 3. So negative 5 over 3. And again, the power on that factor is 1. So here I have multiplicity 1. Multiplicity, I'm just being lazy, not writing out the full word. It's multiplicity. Multiplicities. And finally, if I have 3x minus 5 is equal to 0, I can add 5 over here. That's positive 5, and then divide by 3. So positive 5 over 3. So here, that one's going to have multiplicity 1 as well. As a quick double check, remember your original polynomial function had a degree of 5. If you add your multiplicities, that should give you 5 also. 2, 3, 4, 5. Okay, so we haven't made any major mistakes anyway. All right, so whenever you're going to graph a polynomial function, the first thing you want to do is factor it. And then from that factorization, you can find the zeros and their multiplicities. From here, you are practically done. Remember what you need when you're going to graph a polynomial function. You're going to need the x-intercepts. How do you find x-intercepts? Well, you set y equal to 0. Well, you just did that. That's what this is. All right? Here's your polynomial function. You set y equal to 0. Oh, and you found your solutions. So already we have our x-intercepts. We have x-intercepts are going to be 0, 0. Notice these tell me what the x's are. The y has to be 0. That's what we mean by an x-intercept. So 0, 0, negative 1, 0, negative 5/3, 0, and positive 5/3, 0. The multiplicities, don't throw those away. We're going to use those in a little bit when we graph, but for now I'm just writing down the points. All right, aside from the y-intercepts, aside from the x-intercepts, we need a y-intercept. Okay, well, you do that by setting x equals to 0. Okay, well, let's go back to our original function here. If f of x is equal to all this stuff, well, let's plug in 0. F of 0 is equal to 9 times 0 plus 9 times 0 again, minus 25 times 0, minus 25 times 0 again. Oh, well, that's going to be 0 plus 0 minus 0 minus 0. Yeah, that's going to be 0. Okay, so I have my y-intercept. That's going to be 0, 0. Notice that in this case, the x-intercept, the y-intercept is also one of the x-intercepts. That'll happen once in a while. That's okay. It won't always happen. In fact, it won't even usually happen, but it will happen from time to time. The y-intercept might also be one of the x-intercepts. And then don't forget your end behavior. Your end behavior, right here, 9x to the power 5. That's the only term that's going to matter. The end behavior comes from the lead term, the term with the biggest power. Note that this has a power that's odd. So here, n is odd. And the coefficient is positive. So whenever you have an odd power and a positive coefficient, your end behavior tells you you're going to be going up to the right and down to the left. So that's our end behavior. Just like that. So now we have everything we need. We can put this on our graph. We can plot all these points along with our end behavior and form a graph. So let's go ahead and plot this. All right, let's start with our points. We have a y-intercept of 0, 0. Okay, well, that is on the y-axis. Notice that's also on the x-axis. So again, as we said, that is also one of the x-intercepts. We also have 3 other x-intercepts. 1, 2, 3. 1, 2, 3. And that's going to be negative 1, 0. Negative 5/3, 0. Negative 5/3 is the same as negative 1 and 2/3. So back 1 almost all the way to negative 2. So right around there. And then positive 5/3, 0. Positive 5/3 is 1 and 2/3. So 1 and 2/3, almost all the way out here. Now, if you divide 5 by 2, you get 1 with a remainder of 2. So 1 and 2/3. All right, so we have these 1, 2, 3, 4 points. And we have our end behavior. Here's how you use end behavior. End behavior tells you what happens once you get past the last intercept. Meaning, if once I get to the right of the rightmost intercept, the graph's going to look like this. Once I get to the left of the leftmost intercept, my graph's going to look like this. So once I get, here's the rightmost intercept. Once I go to the right of that, my graph's going to look like that. Here's the leftmost intercept. Once I get to the left of that, my graph's going to look like this. Maybe I should label some of these numbers, yeah? 2, negative 1, 1, 2, like that. And there we go. So our end behavior, up to the right, down to the left. Up to the right, down to the left. Okay, so now the question is, what happens in the middle? Well, obviously we have to go through these points. Well, yeah, obviously we have to go through those points, but not obviously how I'm supposed to do that. For example, okay, I'm going to connect from here to here. Am I supposed to do that? Or should I go up really high? Or maybe I'm supposed to go down like this. Or maybe really far down. Or maybe I'm supposed to go right across. You know, I don't know. Same thing between here and here and between here and here. I don't actually know what happens between them. I know my graph has to cross through the points, but I don't know exactly how. So here, we will sometimes graph all of the information that we found and still have some questions. Still not sure exactly what should happen between the information that we found. For that, we have one last piece of information we can use, and those are called test points. Quite literally, we're going to just pick some numbers and test to see what happens. So right here, what I'm saying is that I know what happens when x is equal to negative 5/3. And I know what happens when x is equal to negative 1. Okay, but I want to find out what happens in here. Okay, so pick a number in here. I'm going to pick a number between negative 5/3 and negative 1. It doesn't really matter what we choose, but I'm going to choose something that's nice, or at least as nice as I can. Here I'll choose negative 1.5. Right here, negative 1.5. Okay, so let's say x, so if x is equal to negative 1.5, negative 1.5, negative 3/2, however you want to say that, we can plug that in and figure out what happens for y. Same thing here. We don't know what happens between negative 1 and 0. Okay, so maybe plug in negative 1/2. If x equals to negative 1/2, and that'll tell us what happens between here and here. Notice we don't really have any number in particular we need to use, just something in between here. So may as well keep it as simple as possible. Here I need some number between 0 and 5/3. Well, I'm going to use the number 1. I could use a half also, but again, I want to use the simplest number that I can get away with. So if x is equal to 1, let's see what happens. These are called your test points, and they're quite literally just testing to see what happens. You pick some numbers and plug them in and test to see what happens. All right, so let's just take these numbers and plug them in. We're going to plug them into our original function here. It depends on your preference. Some people prefer to plug them into this version of the function right here. Other people prefer this version here. They both have their merits. This one is it is a little more straightforward. You're literally just plugging into these 4 values and then just going straight across. On the other hand, this one can be a little bit simpler if we recognize that we're evaluating each piece on its own and then multiplying. So it is a personal preference. Obviously, both of these mean the same thing. This one came from factoring this one, so just pick whichever one you think is more convenient and plug it in. I'm going to go ahead and use this one down here. That's just, again, my personal preference. All right, so if x is equal to 1, then f of 1 is equal to, well, let's see, that's going to be 1 squared times 1 plus 1 times 3 times 1 plus 5 times 3 times 1 minus 5. And again, all I did was I took this factored form. I took this one, x squared, x plus 1, 3x plus 5, 3x minus 5, and wherever there was an x, I just plugged in a 1. All right, so let's see, that's 3 minus 5 is negative 2. 3 plus 5 is 8. 1 plus 1 is 2. And then 1 squared is 1. And now those are all being multiplied together. Negative 2 times 8 is negative 16. Times 2 more is negative 32. Times 1 more is still negative 32. So there we go. We have our value. If x is equal to 1, y is equal to negative 32. So if x is equal to 1, y is equal to, I guess I'm going to have to count by 5s or something. 5, 10, 15, 20, 25, 30, 35. So let's see, negative 10, negative 20, negative 30. Okay, so if x is equal to 1, y is equal to negative 32. So right about there. Okay, so now I know exactly what needs to happen. I know from here, I'm going to connect from this point to this point by coming down by that much. And I'm going to come back up. Let me draw that so it's a little smoother. These graphs are supposed to come out nice and smooth and straight like that. There we go. Just like that. Here I'm making the assumption that this point is as low as the graph gets. That's not always true. It's possible that it comes down to this point, goes down a little bit further, and then comes up. But that's not something we can test right now. For those of you who go past algebra into trigonometry and calculus, there's more stuff you'll learn about functions and their graphs in later courses. For right now, we're going to say, okay, it's going to come down to about right here. Is that exactly where it's supposed to come down to, or is it supposed to go through here a little bit further down and then come back up? Well, actually, we don't really have a good way of telling that right now. So for now, that's close enough. Okay, and we can do the same thing here. We can plug in negative a half. So an f of negative a half is negative a half quantity squared, negative a half plus 1, 3 times negative a half plus 5, and 3 times negative a half minus 5. Okay, so that's going to be negative 3 halves minus 5. That's negative 3 halves minus 10 halves. That's negative 13 halves. Negative 3 halves plus 5, or in other words, negative 3 halves plus 10 halves, that's 7 halves. 1 minus a half is a half. Negative a half squared, negative 1 half times negative 1 half is positive 1/4. And if we multiply all those together, positive times a positive times a positive times a negative is a negative. 13 times, oops, let me scoot that over a little bit. 13 times 7 is 91. Times 1 is not going to change that, so that's negative 91. And then 4 times 2 is 8. Times 2 is 16. Times 2 more is 32. And if you divide negative 91 over 32, that's about negative 3. It's negative 2 point something. Here, this is, let's see, what was that number? Oh, sorry, negative a half, comma, negative 91 over 32. So if I go back a half, I'm going to go down negative 91 over 32, which is about negative 3. So just a little bit. Remember, that's negative 5. So about negative 3 would be right there. So again, we're not sure if that's the lowest point, but the lowest point is going to be somewhere around here. So here we're going to make the assumption that that's close enough, like that. So here, that shouldn't have gone up. It should go down, but only just a little bit. And finally, this last one. Let's see here. I guess I'm running out of space here. Then f of negative 3 halves is equal to negative 3 halves squared times negative 3 halves plus 1 times 3 times negative 3 halves plus 5 times 3 times negative 3 halves minus 5. Like that. Okay, so negative 3 halves squared, negative 3 times negative 3 is positive 9. 2 squared is 4. Let's see, negative 3 halves plus 1 is negative 1 half. Negative 3 halves times 3, that's going to be negative 9 halves. Negative 9 halves plus 5, that's negative 9 halves plus 10 halves. That's just going to be 1 half. And then that's also negative 9 halves minus 10 halves is negative 19 halves. And now we can multiply. Double negative makes that a positive. Let's see, 9 times 19, that's 171. Like that. And then our denominator, 4 times 2 is 8, times 2 more is 16, times 2 more is 32. Just like that. And if you divide that, 171 divided by 32, that's about 5 point something. That's 5 5 1/4, give or take. So here, that's if x is -3/2, so right about there, then the y value is about 5 point something. Right? So okay, that's +5, 10, 15, 20, 25, 30. So here that's going to be up 5 point something, so just above that line right there. So maybe right around here. And so now you can connect your dots, and that completes your graph. The last thing to mention here is when we found our zeros, we found these numbers. These numbers told us the location of our x-intercepts. Along with those numbers, we found multiplicities. Those came from the powers of the factors that gave us those numbers. Okay, so what about them? Why did we find them? What's their purpose? What they do is they allow us to confirm the shape of our graph. Whenever you have something that has an even multiplicity, let's go ahead and write that down here. If a 0 has an even multiplicity, then the corresponding intercept is what's called the touch point. On the other hand, if a 0 has an odd multiplicity, then the corresponding intercept is what's called a through point. Okay, so what does that mean? Well, this is the only one that has an even multiplicity at 0. All the other ones have odd multiplicities. Let's look what the graph looks like. Notice that at 0, your graph hits that point and then bounces back the direction it came. It started from the bottom, it hit that point, and then it came back down. Notice that all of the other ones don't do that. All the other ones go right through. Here you start from the bottom, you go through that point and come up. Here you start at the top, you go through that point and you come down. And over here you start at the bottom, you go through that point and you continue up. This is the only one where you don't go through, you touch the point and then come back in the direction you started from. That's what those words mean. A touch point is where the graph basically turns around. It touches the point and then it comes back. A through point, well, it goes through. That's a point where your graph is going to go through. So here, this is a through point because your graph crosses right through. This is a through point because your graph crosses right through. This is a touch point. It doesn't go through, it touches it and then comes back. And here, that's a through point because, again, your graph will cross right through at that point. The phrase through point, depending on the book that you're looking at, they also sometimes call it a cross point. And again, same thing. It crosses through the graph. They pretty much separate the two words, right? It crosses through the point. Oh, so some people call it a cross point. Some people call it a through point. All right, so either one. So here, whenever you have the multiplicities of your zeros, they can be used to confirm the shape of your graph. Basically, here, at 0, 0, I'm expecting there to be a touch point. Okay, yeah, that's a touch point. It doesn't go through, doesn't cross, it just hits the point and then comes back. If I ever have a multiplicity that doesn't match the behavior of my graph, then I know something's wrong. So the multiplicities can be used as a good double check. They can be used as a quick way to make sure that I didn't make any major mistakes. The multiplicities should match the shape of the graph. If they don't, well then clearly something is wrong. So to summarize, if we're going to graph a polynomial function, start by factoring it. For now, everything that we give you will be factorable. in later sections, we'll show you what happens if they're not factorable in a traditional way. So start by factoring. Once you factored, find the zeros and multiplicities. And then from there, that'll give you the x-intercepts from the zeros and the multiplicities. You can just plug in x is equal to 0 to find your y-intercept. And the end behavior, that comes from just the leading term. That doesn't involve any of the factoring that you've done. Note that for the most part, this is just something you can observe. You don't have to work for it. You just look, make sure you know where you're looking. The y-intercept is very little work. You're just plugging in a number. The one that does take a bit of time and effort is the x-intercept, and that's normal. That's usually the case. Once you have your x-intercepts, your y-intercepts, and your end behavior, you plot all of those, and then for whatever pieces you're still missing, you plot some test points. Sometimes your test points have to be fractions. That's the way it's going to work for that particular problem, but try to choose the simplest numbers that you can. Here I had a choice of numbers between 0 and 5/3. I chose 1 because 1 is a lot easier than any of the fractions that I might have had. Here I needed something between 0 and -1. Okay, well, I don't have a choice. It has to be a fraction. But I chose -1/2, which is a lot simpler than choosing -17 over 406, or any other strange fraction that I might want to use. Even if you're forced to use a fraction, keep it as simple as possible. Once you have your x-intercepts, your y-intercepts, your end behavior, and any test points that you need, you really only need one test point in between each interval that you are missing. Connect your dots, and you have your graph. Don't forget that your graph should be a smooth, continuous line. Polynomial functions are said to be continuous functions, meaning, well, actually that has a much deeper meaning, but for now, suffice it to say that the graph will be an unbroken line. There shouldn't be any holes. You shouldn't have anything missing. There shouldn't be any jumps from one part of the graph to the other. You should be able to get from one end behavior to the other without ever lifting your pen. For any polynomial function, that'll be the case. And that's it. Make sure you practice these a lot. These have a lot of detail that go into them. These are somewhat longer problems that you may be used to from previous sections or previous chapters or even previous courses. So practice these. Remember, these are multiple part problems. If anybody has any questions, comments, problems, please make a note of those. Reach out to me, come see me next time we meet, or go ahead and send me an email. I hope everyone has a nice day, and please keep practicing.